Welcome back for Module 9b. We're going to be looking at measurable quantities in conjunction with those Maxwell relations and the fundamental relations. So, we know that the natural variables for h are s and p. But what if we wanted to know how h changes in terms of both changes in t and p? Well, calculus is very helpful at this point. So, change in h, dh, is the derivative of h with respect to t, holding pressure constant times dt, plus how h changes with p, holding t constant, times dp. That's fine, but what on earth does any of this mean? Well, the good news is dh dt at constant pressure, I've seen that guy before. We named him C sub p. But what about that dH dP at constant temperature? Well, let's go back to the fundamental relation for H. When in doubt, we always go back to the fundamental relations. So, H has the differential dH equals TdS plus VdP. I can use this to create a derivative by taking, instead of the differential, take the derivative with respect to p, holding t constant. So I do that for each of these, t, ds, dp, holding constant t instead of the differential of s, plus v, dp, dp, holding t constant instead of dp. Well, clearly dp, dp, how does pressure change with pressure? It's just the constant one. So the last of these is clearly v. So I have T ds dp at constant temperature plus volume. Well, this is an unfortunate looking expression, isn't it? I mean, it's got entropy in it. So if we want to change it to those measurable quantities, I need to get rid of the s. So we look for a Maxwell. And sure enough, on that list, ds dp at constant temperature happens to be equal to negative dv dt at constant pressure. And so dH dP at constant temperature is equal to, well, I just switched the order, V minus T dV dt at constant pressure. And I've found then an expression for this in terms of things that are all measurable. Just take this, substitute it in. This one is really better known as Cp dt. This is the expression V minus T dV dt at constant pressure. Now, these are all measurable, but it does require me to know how volume changes with temperature. Okay? If I have an equation of state, I can take the derivative of V with respect to T holding pressure constant. And that's certainly an approach that we can take, and many times that will be what we do. But there are some other ways where there are numbers that I could just look up. Okay? For many substances, I can just look up these quantities. So the things that we can potentially look up, the things we call measurable, are pressure, volume, and temperature, certainly. C sub P and C sub V, those are well-defined, well-established. You've been using those in other courses. And so C sub P is dH dt at constant pressure. It also is equal to T ds dt at constant pressure. C sub V is du dt at constant volume, or it is equivalently equal to T ds dt at constant volume. So if we ever see any of these derivatives, we can just immediately replace them with Cp or Cv. Now there are two others that you probably have not really encountered yet. They are how volumes change with changes in temperature and pressure. And the beta is called volume expansivity. It's how volume changes with temperature at a fixed pressure. Okay? That divided by volume is what is known as beta, or the volume expansivity. Isothermal compressibility, which is not the same as the ideal gas law, the Z compressibility factor. This is a different one. But how volume changes, in this case with pressure holding temperature constant. Now, if I apply additional pressure to something, it's going to decrease the volume, so therefore this has a negative in front of it for the definition of isothermal compressibility. So dVdP at a fixed temperature divided by volume with a negative sign, so that I realize that as I apply additional pressure, it's going to get smaller. Now, these last two are rarely tabulated, but occasionally we can. More often we will end up, indeed, differentiating the equation of state. They are, however, what are called measurable quantities. So let's look at using some of these. So how did H change with temperature and pressure? We started with this, and then we played some math tricks using definitions of measurable quantities and the Maxwell relations to develop this equation. And then we can use this to find that this is beta times the volume, and I can end up with an expression like this. If I did have a table that had beta in it, these things are all things I could look up. Okay. The other thing that's interesting to do is look and see what happens if I apply this rule to an ideal gas. It's a simple case where I can do the differentiation of the ideal gas law. For an ideal gas, V is RT over P, and the derivative of V with respect to temperature, while pressure is constant, now R is always constant, so R and P are constant. So I have R over P times T, and the derivative of that with respect to T is just the constant R over P. So if I plug that in, I end up with C sub P dt minus V times, or plus, V minus R over P times T, okay? But R over T times P, I just said that was the ideal gas law, that's V. So I've said V minus V. That is 0, and so for an ideal gas, dH is Cp dt, which is a result that we have been using quite successfully for some time now. So how about S? How does S change with temperature and pressure? Well, again, let's just simply apply definition of a differential. Okay, go back to our calculus. ds dt at constant pressure dt, ds dp at constant temperature dp. ds dt at constant pressure is related to C sub P. It is, in fact, C sub P over T. ds dp at constant temperature, well, that one's not quite so pretty, but I've got Maxwell's for this. So look at the ones for P and T, and I end up with negative dV dt at constant pressure. Again, this can be related to those measurable quantities beta. This is beta V, and so I can rewrite it in this way if I wish. Either of these last two are typically considered final stopping points. So let's apply this to an ideal gas. We've seen relationships like this before, so let's make sure that this gets the result we expect. So Cp over T, not a problem. It's that dV dt over P, there's the weird one. Okay, but if we apply this to an ideal gas, all right, then, wow, okay. dV dt at constant pressure is going to be, we can just come back to our previous slide back here. dV dt at constant pressure is R over P, okay, and R over P is equal to V over T. And so we end up with either of these two expressions here. We've seen these. This is what we typically use as the definition of ds. Frequently we use it for the case of constant C sub P, and where we say delta S is Cp ln, with the natural log of T2 over T1, minus R times the natural log of P2 over P1. This is a way that that expression can be derived. So next let's look at how U changes with temperature and pressure. So U is H minus PV. du is dH minus PdV minus VdP. We've done all this before. Okay. I could have also started just with the fundamental relation, but I'm looking for how this changes with T and P. So let's apply calculus, du dt at constant pressure dt, du dP at constant temperature dP. So now then, let's look at each one of these pieces. And to do that, this is where the fundamental relations come in handy. So dH dt at constant pressure I've already derived, which is why I chose to work with this form right here. So dH dt at constant pressure minus P times dV dt at constant pressure minus V dP dt at constant pressure. Okay, so let's take a moment and think about this one, this grouping right here, V times dP dt at constant pressure. I'm looking for how pressure changes if I hold pressure constant. It doesn't, exactly. So that's why we say minus 0. So this little group here is gone, and I'm left with these two pieces, and I already have an answer for this. Okay. If I look at the other grouping, du dP at constant temperature. All right, again, taking this just definition up here, dH dP at constant temperature minus P dV dP at constant temperature minus V dP dP at constant temperature. Oh wait, how does pressure change with itself? 1. So we end up with a minus V right here. Again, we've already calculated this, and dV dP at constant temperature is beta T. No, that's the kappa, sorry. This is the V times kappa. And so we end up with this expression here. This we already knew, and we can rewrite this in this way here. Okay. So what about if it's an ideal gas? Well, for an ideal gas, I can take derivatives. V equals RT over P, take the derivative with respect to T, and I end up with, this is just 1 over T. Similarly for this one, I end up with the derivative is the RT over negative P squared, which when I put that all together, I end up with just a 1 over P. There's a negative sign missing right there. This turns out to be positive 1 over P. If I throw those things into my formula I just created for du, Cp minus Pv over T, so that's Cp minus R, plus V times P times 1 minus P, minus 1 over T times T, that's 1 minus 1. So I have Cp minus R plus V times 1 minus 1. 1 minus 1 is 0, those go away. Cp minus R, you might recall that we derived in your definitions of entropy, that this is the definition of CV. So we're going to pause the video here, and when we come back, we're going to look at some additional examples with a few additional math tricks that we're going to need.